Hello, this is Unit 5.1. This is the Atomic Theory Unit. So good news for you. If you're somebody who does not like doing calculations, well, good news is you are done them. Atomic Theory Unit is all theory-based. There are no hard numbers with it. So you don't need your calculator anymore. You do still need your data booklet, but you don't need to do any calculations anymore. So no more conversions, no more moles, nothing like that. It's completely a separate unit. So for those of you who are not into calculations, well, this is the unit for you. Okay, so today's lesson is going to be a little strange. It'll all be, as I mentioned, theory-based. There will be a video with it to kind of watch, to kind of put things into a better perspective. And there's no worksheet with it. Again, it's all just theory, and then next class we'll kind of connect all of the big pieces. So we'll talk about that. Okay, so atomic theory. So here we go. This is your last and final unit for Chemistry 11. This is 5.1. So most popular science pictures of the atom show electrons moving around a nucleus like planets, for example, would around a sun. It turns out these pictures are false. They're not true. These ideas come from an old idea of the structure of the atom and have lasted partly from habit and partly because the modern view of the arrangement of electrons in the atom as we know it today is too difficult to draw simple pictures of. And so we've all seen this image in textbooks and, in some movie where they're in the laboratory and someone has drawn on the board some numbers, then you see this kind of picture. Well, this is actually a very old picture. This is closer to the beginning of the 20th century, the maybe 1910s, 1920s. So it's a very old idea of the atom. At one point, we thought it was this way, and today is not as we know it. Now, you might, of course, say, well, I know it isn't like this. The electrons are arranged in a particular pattern. For example, in a diagram like this one for sodium. This you probably learned in grade 10. And in this kind of diagram, you've got your nucleus, and then you've got your specific orbitals in which your electrons are placed, and then they go around the atom in these very specific orbital pathways. And it turns out, this model we taught you in grade 10 is also false. Now, it's not accidental, and it's not to be mean. The reason why we have given you a model that is not true is not because we want you to learn something that's wrong, is because at that moment in your education, in your chemistry understanding, we kind of give you information that you're able to, actually work with and synthesize and do your actual chemistry with. And of course, as you get older and your knowledge base grows as well, we then kind of show you more of the actual picture as it is. Kind of like, a lot of parents don't tell their kids, they tell their kids about Santa. They don't tell their kids about Santa because they want to be mean. It's just it's a way to, understand that they're getting gifts from their parents without actually telling the kids. And so, of course, they add some sort of, excitement to it. We didn't do it for that in grade 10 for that reason, but we did give you this model because at the time, this is what we felt you could work with, you could understand, and make sense of the atom. So it turns out this model, as I mentioned, is also false. Now, when it comes to these circles here, or these orbitals, they may not be true, but they do represent something that is true, and that is they represent energy levels. And the electrons on the circle closest to the nucleus, they have the lowest energy levels, and this is true for the atom as we know it today. The next electrons in the next orbital, the next 8, for example, they are at a higher energy level, and therefore they have more energy than those in the first. And then on the third orbital, that electron has the most energy of all of those energy levels. Okay, so it's this idea that the electrons, as they get further away from the nucleus, they have more energy because it takes more energy to place them there. Okay, so that part of the model does hold true, but the rest of it is false. Okay, so again, taking a look at this model here of an atom, the way you learn it in grade 10. Again, each orbital is something you can now think of as more of an energy level. And again, the electrons on it have that corresponding amount of energy. Okay. So one way to interpret this is we could literally take the orbitals, kind of imagine you had like wire cutters and you cut them like wires and you straighten them out. those electrons on the closest to the nucleus in the first orbital would have the lowest energy. Those electrons in the second orbital would have the second most energy, and that electron on the third most orbital would have the most energy. Again, as you get away from the nucleus, your electrons have more energy. So that part of the model does still hold true today. Okay, so keep that in the back of your head. Okay, so we talked about how the electrons were not actually moving around the nucleus in the ways that have been depicted before, the ways you learn in elementary school or the ways you learn in grade 9 or grade 10. And the question is, well, how are they actually moving around the nucleus? Well, the simple answer is we do not know. The reason why is a bit more complex. It's not that we simply don't know, it's more that it is impossible to know. And let me tell you why. Okay, so in grade 10, as mentioned before, we gave you this kind of model of the atom. We said, okay, think of your solar system. The sun is like the nucleus, and the planets are like the electrons orbiting it. The difference is, in the solar system, I can look at a planet, and using math and physics, I can figure out where that planet is going to be 2 years from now, 100 years from now, 10,000 years from now. Why? Because the planets orbit the sun in a predictable pattern. Okay? I can know exactly where my planet is going to be. I know exactly whether, again, that's a day away or a million years away. The Aztecs, the Greeks, they all knew exactly when, all the planets would line up to create an eclipse, or, where a particular planet would be at a certain time of the year. They could do this because the planets literally went in fixed paths around the sun. And so this kind of holds well to the model you learned in grade 10, right? You knew if you had your electrons in your orbitals, just like the planets around the sun, you knew exactly where they were going to be when they were in that orbital. The problem is we cannot do that for electrons. Why is that? Well, simply put, to plot an orbit, you need information. You need to know things like, where is the electron? Which direction is it headed? How fast is it going? Okay, those things we can do with planets, because not only can we observe them and know these things, but they do this in a predictable fashion. Okay, the problem is we cannot do these things for electrons. Well, why is that? Okay, so let's get to our next part. The reason why is something known as the Heisenberg uncertainty principle, which says loosely that you can't know with certainty both where an electron is and where it is going next. Okay, so what I've done is I've included a link here to a YouTube video. You can simply copy and paste this into your, if you're at home, actually, you know what, let me just add this in here to the notes. You can simply type, I'm trying to think of a shortcut. You know what? Hopefully you can just copy and paste this. I'll post this into the team chat. That way you can just copy and paste it. I want you to watch this video and do not stress out over knowing everything in it. A lot of the material in it is material that is at the university or college level of physics. So I obviously don't expect you to know it. I just kind of want you to listen to it, look at it, to kind of, they do a very good job explaining it, don't get me wrong, but at the end of the day, I don't expect you to know all this physics stuff. Okay, it's really, I'm just going to give you the why and the how of this Heisenberg uncertainty principle. But anyway, take a look at the video, do your best when watching it, and then once you're done it, come back and I'll try and explain it in my own words in as simple a fashion as possible. Okay, so take a look at this video and come back once you're done. Okay, so hopefully you watch the Heisenberg uncertainty video. Okay, what are the big things you can pull from it? Well, the big things you can pull from it is simply this. Anytime you're using technology to detect something, where something is, how hot or cold something is, or any type of sensory equipment you use energy to do this. For example, if I want to detect your body temperature and I give you a thermometer, well, when I give you the thermometer, I'm basically looking at the transfer of energy from your body to the thermometer. Or let's say I want to see where an object is in the dark and I use a flashlight. When I use a flashlight and I shoot beams of light onto an object to see it, I'm now giving that object energy. And so anytime we try and detect something, we're basically using energy to do this. Now, when you do this on a person, it's not a big deal, or a car. So, for example, as they mentioned in the video, if you're a cop and you're detecting the speed of someone on the car, you shoot basically a wavelength of light at the car, it shoots it back at the radar, and it can determine how fast you're going. When it does that, it doesn't really change much about the car because the car's wavelength is so short. Versus something like an electron, which is so small and it's such a big wavelength that when I shoot it with a beam of anything to figure out where it is, a light or some sort of energy or something, when that energy hits the electron, it basically, so let's say the electron's going in a perfect straight line and I hit it with a beam of energy to figure out where it is, all of a sudden it can go to the left, it can go to the right, it can go up, down, it can go twirling in a circle, who knows? It can go all sorts of directions. What happens is, by you trying to figure out where the electron is, you completely mess up everything about it. You can no longer figure out where it is anymore. And so this is the Heisenberg uncertainty principle. It basically says that once you try and figure out where something is, you change it. And once you change it, your information doesn't work anymore. It's no longer good. And so this is a problem with the atom, is that we don't know both where an electron is and where it's going. Because as soon as we try and detect something about it, we add energy to it, and then that just puts it somewhere that we don't know where it's going to be. And so it kind of messes it up. So for electrons, it's tough. We basically can't figure this out. But there are some things technology does allow us to do. One of those things is there are pieces of technology out there that allow us to determine a relative immediate location of the electron. Not where it's going, but just where it is at that moment in time. Okay? And typically, this will allow us to figure out where the electron is going to be most of the time, or what we call an orbital. So in grade 10, orbitals were simple, or even grade 9. I said to you, draw a circle. On the circle is like a trail when you go hiking, right? It's like, here's the woods. Somebody has cut down the trees along this path. It's a perfectly defined path, again, like a street or a sidewalk or anything that you follow. You can go around it 1 billion times or 1 million times. It's the same path, right? That's what we taught what an orbital was in grade 9 or grade 10. Well, it turns out that's not true. That's a lie. Electrons don't follow paths. There's no road they go down. There's no sidewalk. There's no path through the forest. So when it comes to electrons, it's a little more complicated. Orbitals, in fact, are not defined paths. What they are basically, first of all, they come in different shapes and sizes, which is very different than what you learned in grade 9 and grade 10. Remember in grade 9 and grade 10, we said, oh, every orbital is just a circle, right? Well, that's not true at all. That's a lie. We told you that out of simplicity. An orbital is going to be defined simply as any area of space around the nucleus where you're more likely to find 95% or higher chance of finding an electron there at any given time. So basically what an orbital is just an area of high probability of finding an electron. And so, again, as I mentioned, if an electron is in a particular orbital, you can know about its energy relative to where it is close to the nucleus. Because remember we said the closer you are to the nucleus, the lower energy you have. The further away you are, the more energy you have. But there is no way of knowing how it is moving within that actual orbital. Okay? So this makes things very difficult for us. But it does give us kind of a growth to our atomic model. So in grade 9 and grade 10, hopefully you may have discussed a little bit of the history of it, but starting with us thinking about, with Dalton, thinking that atoms are just spheres, super simple. And then Thomson come along saying, well, okay, we think of them as spheres, but they have charges in them. There's some negative things and some positive things, okay? And then Rutherford comes along and says, okay, yes, there are negative and positive things, and in fact, all the positives are in the middle in something called the nucleus, and then the negative things, the electrons, are orbiting around it, okay? That's kind of something we learned in elementary school. Now we get into grade 10 and grade 9. You learn the Bohr model. In the Bohr model, these electrons travel around specific orbitals or paths around the nucleus. Okay, well, we know the electrons go around the nucleus, but it turns out there actually aren't specified paths. And now we come to the actual current model of the atom, what is known as the quantum model. In the quantum model, the electrons still orbit the nucleus, but they orbit the nucleus in not specific defined areas like they are, again, circles. They are all sorts of different shapes and paths around it. And that's what we're going to talk about today. So it's going to get a little weird, and that's okay. I don't expect you to know everything by the end today, but I just want to introduce the topics to you. And then, of course, as we go through it, we will kind of elaborate on more of the details and make more sense of them. Okay, so how are we going to visualize the atom from now on? Okay, so I want you to imagine that you had a single hydrogen atom. So hopefully you know hydrogen is atomic number 1. So it, of course, has 1 proton and 1 electron. So again, we've got our proton that is our nucleus, and then you've got some electron that is orbiting it in some sort of pathway, okay? Now, what we're going to do is we're going to do a very simple thing. I'm going to take a picture of my electron at one moment in time. So just this little, let's just do a red dot here. Oops, red dot. And outside red dot. Okay, so this is our electron. So I take a picture of my atom. There's my electron. Okay, guess what? On the second passes, I take another picture of my electron. Now it's over here. I'm going to superimpose the image. So I'm not resetting the image every single time. I'm basically superimposing it. The image before, the new image is put on top of the image from before. Okay, I take another picture. Oh, there's the electron. I take another picture. There's the electron. I take another picture, and there's the electron. And I keep doing this, okay? I don't do this 5 times. I don't do this 10 times. I don't do this 100 times. I can do this, a few thousand times or however many I want to. But what happens is after a while, you start to notice that a certain picture emerges around the nucleus. What happens is as I superimpose the images of where the electron is, I start to notice a pattern. And the pattern I start to notice is that the electron is typically in a certain area away from the nucleus. It may not be a perfectly defined path, but it is in a certain area. So if I look at my picture right now, I've only taken, I don't know how many are here, let's just say 20 pictures. You notice the electron is never over here, and it's never right here. It's usually somewhere around this far from the nucleus. And what happens is this picture starts to give us an idea of where we're going to find the electron most of the time. In essence, it acts as an orbital. Okay? So what we do is we keep on taking this picture over and over again, and eventually we build up a kind of 3D map of the places the electron is likely to be found. In the case of hydrogen, again, we will typically find this electron anywhere within a spherical space surrounding the nucleus. And again, how do you define an orbital? Well, now an orbital is not just a pathway, it is simply a mathematical probability. 95% of the time, or greater probability, that I'll find an electron in this particular given area or region of space. This is called an orbital now. Okay, so again, orbital is a region of space, and basically you're going to find the electron 95% or more of the time. So this changes now how we think of the electron, okay? This is not a rigid, so if I draw here, here's grade 10, right? Here's my, oops, let me just take that out. There's my orbital, right? And my electrons are going to be on the orbital, all right? Well, that's not the case anymore. This is not a defined thing. It isn't like it has a border or an edge or an exact path. It is very diffuse. Okay, it's not exactly a solid kind of thing. And so now we think the electron's orbiting the nucleus rather in like an electron cloud. At any given time, I can find the electron here or here or here or here or here. But again, it's not fixed. Again, I can keep taking more of this picture and keep making more and more of these dots. And again, over time, again, you would just see this picture be a little bit more clear. Maybe once in a while, I will find an electron over here, but 95% or more of the time, that electron is relatively pretty close to our nucleus in kind of a spherical area. And again, if I were to actually kind of draw the shape, I'll use a freehand tool, it's kind of like a cloud, right? It's not exactly a perfect kind of orbital. Oops, so that doesn't look pretty. Not perfect kind of orbital here. Okay, so it's this idea, it's kind of spread out like a diffuse cloud. There is no defined edges. It's just a general area. So here's an actual representation of it. If you notice, in this 3D map someone built around a particular atom, when they took pictures of the nucleus, you notice the electron is rarely found here. It's rarely found here, or here, or here, or here. Yes, coming closer, you find more of it, and coming closer, you can find more of it. So you notice this area in here is going to be considered its orbital, because it's where you're going to find it 95% or more of the time. Is it a defined area? Is it a perfect circle, a perfect square, a perfect triangle? No. It's kind of a diffuse shape. It's kind of like a cloud. Okay, so it's a very different way of thinking of the electron. Remember, these are not all electrons existing at the same. This atom doesn't have 10,000 electrons. It's just the same picture superimposed over the picture before it, and you just get to see the change of the location of the electron every single time. Okay, so it's a very different way of thinking about the atom than you would have in the past. So again, to bring everything back together, an orbital is simply diffuse. The electron orbits the nucleus in diffuse regions of space, again, which are not rigid. There are no lines, there are no paths, there are no streets, but rather as simply areas of high mathematical probability of finding an electron. So very different than what you learned in grade 9 or grade 10. And again, the reason why we gave you that simpler model is because at the time, that's what you could work with. And now we give you a more complex one because now we feel you can deal with this. Okay, so this is where it starts to get weird. And again, I don't expect, well, maybe it already is weird, but I don't expect you to memorize all this. Just kind of take it in, and then next class we'll start to put all the pieces together as we go through it in detail. Okay, so orbitals. Orbitals are talked about as areas of high probability. Now, orbitals are very different because orbitals aren't these perfect little circles, as we mentioned before. Orbitals now come in all sorts of different shapes and sizes, in fact. What doesn't change with orbitals, though, is the energy level. So that fact still carries from your previous models. Remember, the lower the energy level, your electron, the closer to the nucleus, the higher the energy level, the further it is from the nucleus. So again, what doesn't change with orbitals is that the energy level, again, will usually be defined by how close it is to the nucleus or how far away, okay? And this is connected to the period in your periodic table. It is directly connected to the energy level. If you didn't learn about this in grade 10, we will talk about it in grade 11, so don't worry about that. We will cover it. Okay, so let's talk about our atom and our orbitals. Okay, take a look at this picture of an atom. It looks nothing like you did in grade 10 or grade 9, right? It's really, really weird. The things I want you to focus on are kind of, first of all, in the center is still the nucleus. This has not changed. You'll notice these kind of weird shapes coming from the nucleus. What are those? Those are different orbitals, and orbitals have different shapes. Some are shaped like simple spheres. Some are shaped like kind of long balloons. Some have multiple balloon shapes. Some are like rings. So they come in all sorts of weird shapes. So I will never expect you to draw these out. Okay, so don't ever expect that. Just kind of, again, take it all in, take a look at it, and just see it. I will tell you what to focus on when we get to it, okay? Okay, so it turns out there are 4 types of orbitals, and you must know, the only thing you need to know about those orbitals for right now is just simply their names, okay? And they're really easy. They're simply a letter associated with each orbital. So the first orbital you need to know is called an s orbital. And s orbitals get their name because they have a spherical shape. So you can see in the center here, see that sphere? That's an s orbital. You see this sphere out here? That's an s orbital. So s orbitals are simply spherically shaped, hence why they're called the s. And these orbitals are the first to fill in every single energy level. And an s orbital can hold a total of 2 electrons. And later on you'll learn why that is, and you'll learn how to memorize it. So just for right now, you can write it down, and then later we'll talk about how to figure that out. Okay, for your next one is a p orbital. P orbitals have a very different shape than s orbitals. P orbitals, imagine you took 2 balloons you just filled up. They each kind of have like a bowling ball kind of shape to them. One end is a bit wider than where you tied the knot for the balloon. And about you tied both of the balloon knots together, okay? So it looks like two kind of bowling ball pins attached at the tops. P orbitals can hold a total of 6 electrons. And p orbitals only exist at energy levels 2 and higher. So you do not have p orbitals in the first energy level, but you do have them in every other energy level. Okay, the third type of orbital you need to know is called a d orbital. And if you thought S and P were weird, well, D gets even weirder. D orbitals can hold 10 electrons, and they get filled after your S and P orbitals are filled up. D orbitals only exist on energy levels 3 and higher. Now, how would you describe the shape of it? Well, it's a whole lot of weirdness going on. In one case, it's like a ring with 2 balloons. In another case, it's 4 spheres. In another case, it's 4 spheres. In another case, 4 spheres. In another case, 4 spheres. It's really weird. You don't need to memorize it, but that's what they look like. So there you go. Okay, the final and last one, F orbitals. F orbitals can hold a total of 14 electrons. And F orbitals only exist at energy levels 4 and higher. So how would I describe its shape? I don't know, 6 balloons, 2 rings with 2 balloons. I mean, it's just really, really weird stuff. So again, we won't ever go into this kind of detail. Any of this kind of stuff, you can learn it if you want to take higher chemistry or physics in university or college, but we will not go into that. Just know that it's really weird. So there you go. That's all you need to know. Okay, so those are your 4 orbitals. And again, do I expect you to know exactly everything about them? No, just kind of be aware of the names. Next class, we'll start to get into details, how to kind of connect everything together, and then start to make a bit more sense of everything. Okay, our final and last piece. Again, this is just, again, today's all about theory. So again, just absorbing the information, and then we're going to give you more detail next class. Okay, our last piece here. Now, how are we going to think about our atom? So in grade 10 or grade 9, I'll say to you, okay, here's your Bohr model. Here's an atom of sodium, okay? Place the electrons in the orbitals. Well, that was easy, right? Sodium atom has 11 protons, therefore has 11 electrons. Well, 2 in the first orbital, 8 in the second, and 1 in the third. I'm done. Okay. Sadly, it's not that easy anymore. So atom, how we're going to think of the atom is going to be very unique now. Okay, it is no longer just a nucleus with nice rings around it, because that is not true. So what's another way we're going to think about our atom? Well, I'm going to give you an analogy here, because you know I love to give you analogies. Let's think of our atom like a really weird hotel, okay? And it's shaped like an inverted pyramid. So pointy at the bottom and bigger at the top, okay? Now, we know that the nucleus is at the very bottom. Why? Because in terms of energy, the lowest energy is found closest to the nucleus. So we're going to think of our hotel starting at the nucleus, is basically the ground floor. And then every floor above is another energy level. So the first floor would have the first energy level, the second floor would have the second energy level, and the third floor the third, and so on, okay? Now, what are these floors? Well, in an atom, the floors are basically your orbitals. This is where you're going to find your electrons. Okay, so they are where you structure everything. So the orbitals are the floors, they're the structure of your actual atom. Now, the electrons are going to be placed into those orbitals. And just like in a hotel, if the floors are the orbitals, then the electrons are the people. Okay, they go into those orbitals. And on each orbital or floor are the rooms, right? If you're in a hotel, you stay in the rooms. And our electrons stay in things called suborbitals. Okay, so again, the analogy is the nucleus is the bottom ground floor. Every floor above that is an orbital, and they correspond to the energy level. We then place those electrons into those orbitals, which are like the floors. And the electrons go into the rooms on each floor, which are known as suborbitals. That's where they stay. Okay? So that's the analogy that I'm going to give you. Okay, so as I mentioned, every energy level of an atom, again, is associated with different orbitals and different numbers of suborbitals, which are the rooms. Okay, so every hotel, every atom has a different number of floors or orbitals and number of suborbitals on those floors. This will affect how many electrons can be placed there. So for example, if I compare sodium, atomic number 11, and neon, atomic number 10, in neon I have to place 10 electrons, in sodium I have to place 11 electrons. In neon, I would only need 2 floors, because again, it goes up to energy level 2, which is the second period. With sodium, however, I need 3 floors, because again, it is on the third period. Therefore, I would need at least 3 orbitals there. Okay, so this is going to change a little bit of how we approach the atom. Now, as I mentioned, every orbital has suborbitals, which are where the electrons stay. They're like the rooms. And each suborbital can hold a total of 2 electrons. And later on, when you start to learn about configurations, this will allow us to predict which orbitals are filled and in what order they exist. I know this is a lot of weird stuff, it's a lot of analogies, all this kind of stuff. I promise you, it will make sense once we start actually putting these together. But for right now, I know it's a lot of weird information. You just kind of have to go with the flow and then just kind of pick up the slack as we go through the material. But I guarantee you, I've taught this many times. It starts off super weird. People are oh so confused. So you're not alone if you are. But later on, I promise you, it will make more sense. Okay. So for every single atom or ion from now on, where you're trying to place your electrons, you're going to write something called an electron configuration. An electron configuration is basically a code or a bit of information which not only tells you the energy levels the electrons exist on, but what orbitals they are placed into and which suborbitals are filled. Okay, and that you're going to learn next class. Okay, so today was weird, and that's okay. We had some weird days. So next class, we will make more sense of this. We'll come back to it. And I promise you, we'll make this information, hopefully, make a lot more logical sense to you next class. Okay? There is no worksheet with it or practice with it. That's it. Next class, we will start to then connect these big ideas. Okay. Take care.